Okay, this is a quick video about work, path dependence, and conservation of energy. We're going to talk about what this actually means. Normally, when people say, is a force conservative, they say conservative forces conserve energy. And we want to have something more intelligent to say than that. That doesn't really mean anything. So we're going to start from the basics. The first thing is work. And so work is F dot dx. In other words, physicists decided that when you push something, a certain distance, we want to come up with a phrase for that. So here's somebody pushing something to the right, and they push it a distance x. Okay. Now, the thing to keep in mind is that if you look at other forces acting on the box, those forces may not point along the direction of motion, and physicists say this person isn't helping, so let's not include their force. And so instead, the dot product selects only the part of the force that is along the direction of motion. So dot product has that unique feature. Here's the blue force, it multiplies dx. I'm not moving in the y direction, and the dot product immediately eliminates that force for me, so I don't have to worry about it. Okay, the other thing is, what does work do to an object? Well, if an object starts with zero velocity and you push the object, then sometime later, after a certain distance, the object will have a non-zero velocity. In other words, work speeds an object up. But now, one thing to consider is I didn't say where we started and where we ended. I could just as easily have said that we started over here and we're moving this way. In other words, now I started with a non-zero velocity to the left. The boy is pushing it to the right, and now I slow the object down. In this case, my work is negative. Okay, what happens if the force depends on the distance? What do I do in that case? Well, the force here is a different value than the force here. So really what I ought to do is break it up into smaller pieces and then add all the works from each piece. Of course, if this changes continuously, then I'm going to have an infinite number of things to add, and you know what you do when you need to add an infinite number of things. You do an integral. I want to do this integral right now in general to show you that work has something to do with changing something's speed. So instead of writing f dot dx, since f selects the part of f that is parallel to dx, I'm going to write f parallel dx. And according to Mr. Isaac Newton, that's mass times acceleration. I'm going to show you the standard trick that people do, and that is you rewrite the acceleration as dv dt. You invoke chain rule in order to write dv dt in terms of dv dx. You cancel this x with this x. You call this thing a v. And when you do that, you end up with this remarkable result that without even looking at what the force you're talking about is, it turns out that the work is equal to the change in kinetic energy. Work is change in kinetic energy, and that is why it is such a useful thing. Okay, so let's look at a particular example. Here I have the force vector field for a uniform gravitational field. This is just gravity at the surface of the Earth. In other words, gravity is the same size everywhere, and it always points down. Each one of these points tells me what the force due to gravity is at that point. You know what happens when you throw a ball from the ground? It makes a parabola. It goes up and then it comes back down. A thing to note is that the path that this takes is along the direction of this black curve. The velocity vector at any given point is these red arrows. Now, each of these red arrows has a component that points along the direction of the force. So in this particular case, when I'm down here, my velocity is upward, and the part of the path that is along the direction of the force is this guy. Notice that it points opposite the direction of the force. That means that the work done is going to be negative. That means that the speed will decrease. That is why this velocity vector is shorter than the velocity vector before it. Here, I still have a component that points against the force, and so more negative work will be done, and that is why up here, my velocity vector is still shorter. On the way down, my velocity vector has a component that points in the same direction as the field, and so my velocity vector gets longer. That's the idea. In order to compute the work, what I need to do is do it step by step. The reason I need to do it step by step is, look, this red guy is ds. In other words, our path is constantly changing and pointing in different directions, even though the gravity field, even though F is constant, this guy is the one that changes. So that's a little different than maybe some integrals or changing functions you've seen in the past. This is the thing we're integrating over that changes. Okay, nonetheless, we can still write an expression for it. So this ds is just dx dy. If that strikes you as weird, just imagine that like at any given moment, this is the direction of ds. It is just like any other vector. It has an x component and a y component, and those are, of course, dx and dy. I can expand this out, and what I'll be left with is mg dy. So how do you find the total work? You look at every single point along this curve and you add them up. That means doing an integral. So if you do an integral over our curve C, and this is my curve C, then it's pretty easy to evaluate. You end up with something that looks like m times g times delta y. Now, a thing that is kind of curious about this is notice I didn't really have to say anything about the curve I was on. And you might wonder, hey, wait a minute, maybe you could take a different curve. Okay, here is a different curve. This curve is actually 3 separate curves. And if you think about it, what does this curve do? This curve goes straight up against the gravity field. And so you'll end up with a term that looks again like this. This curve goes perpendicularly to the gravity field. So the work done here is 0. The work done here is less than 0. And then as you come straight down, there's really no integral required because both ds and f are constant along that curve. And it turns out that for this path, even though the work done is greater than 0, I can still use this equation to find the work done on each path. In some sense, what that means is this force field happens to be the same value of work regardless of if I take C1 or C2. Another way to say that is that the integral over a curve of C1 and C2 are equal to each other. This is a big deal. What it means is that for this particular vector field, I can choose any crazy curve I want, and I will always get the same value. That's curious. If the curve doesn't matter, it means that there must be some number here and some number here, and that the work is the difference between those two numbers. Another way to say that is that work is minus delta U. And you may say, why did you put the minus sign there? That's very strange. I thought you just said it was the difference between those two. It is, but I can define this number in such a way that the work is minus the difference of those numbers. And I'm doing it for a very particular reason. You'll see it'll pay off in a second. The point I want to make here is that if the path doesn't matter, then we say that the force field is conservative. Why do I use the word conservative? Well, let's think about this. We already know that the work has to be equal to the change in kinetic energy. And now I'm saying that if and only if it's path independent, then there must be two numbers such that the difference between those is equal to the work. That's because it doesn't matter how I get there, so it can only be the difference between those two numbers. Now, here's a curious thing I can say, that those are equal to each other, and then if I put them both on the same side, holy Toledo, I just derived energy conservation for a conservative force. So do you remember this thing we said earlier? A conservative force conserves energy? Well, okay, now we know what it actually means to be conservative. It means that the integral is the same for all paths. So here's what I want to do in the rest of the video. Here, I had to do a bunch of examples. I still haven't particularly proven that every single path I can show you has the same value. I want to show you how to look at a force and determine, without having to do an infinite number of integrals, whether or not that force is conservative. Okay, so we're going to start out in 1D, and then later I'll show you how to do it in 3D. Okay, so I have a box that starts at A with some velocity, and it moves to the left, and when it's at B, it has some different velocity. And the reason it has some different velocity is because some force is acting on it. In other words, this force has done work on this object, and that work has created a difference in kinetic energy, which ends up meaning a difference in speed. Now, the question is, does this change in speed depend on how we get from A to B? And on the one hand, this sounds a little strange. You're like, what do you mean? There's only one way to get from A to B, and that's go to the left. But actually, what we can do first is go from A to C, and then go from C back to A, and then go to B. And you may say, I don't understand what that's going to accomplish. How could it possibly accomplish anything? Well, let's see. Let's play it out. So first we go from A to C, and then we go from C to A, and then we go from A to B, and that's the same thing. In order for these two to be equal, I need the following condition to be true. I need the integral from a to c plus the integral from c to a to equal 0. If you took your first semester of calculus, you should look at this and you should say, isn't that always true? Well, actually, no. I'm going to show you some examples where it's not true. The real condition we're trying to check here is it the case that the integral over a closed curve is equal to 0? In other words, if I go the integral from a to a, does that equal 0? If I can show that it's 0, then the force is conservative. If I can't, then it isn't conservative. So let's look at a concrete example. You know that if I have a ball and I throw it up into the air, on the way up, gravity does negative work on it. It gets to the top, it runs out of gas, and then what happens? Gravity does positive work on it on the way down. That means that by the time it gets back down to the bottom, it has the same velocity as it had in the top. If I want to write some algebra to describe that, it would look something like this. On the way up, I have negative work. On the way down, I get positive work. W up plus W down equals 0, and hence delta V is 0. So apparently, for gravity, it's a conservative force, okay? But what happens if I add drag? What happens if I add drag? Well, drag doesn't care where you are, it cares how you're moving. On the way up, drag opposes you. On the way down, drag opposes you. And so if I calculate the work again, all of a sudden, on the way up, I have minus mgh minus the drag, and on the way down, I have plus mgh still minus the drag. This isn't 0 anymore. That means that for this particular function, it is not conservative. And you might say, wait a minute, that must mean that in some sense this function is broken. It is broken in the sense that there's more going on in this function than just the x. In other words, this function is broken. The integral isn't the same because, in particular, it depends on the velocity. And we wouldn't say that that's impossible. The drag force is a real force that exists in the real world. So we want to know, how do I know if I look at a force if this is going to happen? So this is what we can say. Drag depends on the direction of the velocity. G only points down all the time, okay? And so U is a state variable and F is conservative. I say U is a state variable because remember our chart, I could say here's U at A and here's U at B. And all I had to say is that if I'm at this location, my U has one value. If I'm at that location, my U has another value. Over here for drag, W is path dependent. W is a path, and F is non-conservative. Non-conservative. So what does that mean? The work for a conservative force is just W at B minus W at A. That's basically the same thing we were saying with U before. Here, W at A and W at B are ill-defined because think about it. I start here, I end here. If I say this is W at A and this is W at B, but then I get different answers when I go different paths, clearly they're ill-defined. There is no such thing in this case. And so what we found out is that the work in this scenario is equal to F dx. That is expressible as dw. If you can write the work as the integral of dw, then that's equal to delta w, and the force is conservative. If you cannot write it that way, then it is non-conservative. This is kind of funny, but another way to say this is if the force is dw dx, you see here's F. If F is dw dx, then dw dx times dx is dw. So if this is true, we actually have a testable condition now. If this is true, then your force is conservative. If it isn't true, then your force is not conservative. And it might not be true, for example, if it depends on velocity. And so that's it. dw is called exact if the force can be written as the derivative of some function. dw is not exact or inexact if it can't be written as the derivative of some function. Okay? Another way to say that is if F is conservative, then the work done is minus the change in potential energy. If F is non-conservative, you actually have to do the integral and you have to specify the curve. I have another video where I work out examples of particular curves. You can watch that video if you want to see some of those technical details. The point is that the total work is the work done by conservative forces plus the work done by non-conservative forces. And so here we have just a slightly different statement of conservation of energy. The change in kinetic energy plus the change in potential energy equals the work done by non-conservative forces. Holy Toledo. That's what your textbook was talking about that whole time. A force is conservative in one dimension if it is a function of position only. Okay, what about 3 dimensions? How do we determine if something is conservative in 3 dimensions? Well, just remember, in 1 dimension, if dw can be expressed like this, dw dx dx, in other words, if f can be written as dw dx, then f is conservative and the work is path independent. In 3D, we want dw to be dw dx dx plus dw dy dy plus dw dz dz. That's just how you find the difference in a function, right? What does this mean? This means that if the work can be written as fx dx plus fy dy plus fz dz, in case you're curious and this feels like a whole new thing, I'm just saying fx, fy, fz dotted into dx, dy, dz, and now I'm making this demand that the force be dw dx, dw dy, dw dz. If you've had 3D calc before, you'll recognize that that is the gradient. If you haven't, it isn't crucial. You just need to understand that the force needs to be able to be written as those vectors. You might say, isn't it always the case that the force can be written like that? Well, I don't know. I'm going to show you some examples where it isn't true. The idea here is the same as before. W is exact if its mixed partials are equal. What does that mean? What I'm saying is, if I take a second derivative of W, then it shouldn't matter which derivative I take first. Essentially, I'm saying d by dx of dw dy should be equal to d by dy of dw dx. That is true if I started with a function w in the first place. That will definitely be true. But if w isn't a function, if it's ill-defined, we may find that that isn't true. So I need one condition to be true for x and y, another condition to be true for x and z, and yet another condition to be true for y and z. This is the same as imposing this condition. If this condition is true, then the force is conservative. Again, if you've had 3D calc, you'll recognize this as the curl of F. If the curl of F is 0, then F is a conservative force and energy is conserved. Energy is conserved. Now, let me give you an example where it is not conserved. Here is a function, minus y x 0. I say, well, maybe this must be the gradient. This must be the derivative of some function. But you see right away that if I take dfx dy and dfy dx, they aren't equal to each other. This is not conservative. And this wasn't even a crazy function. This is pretty easy to come up with. I want to show you what this function looks like. This function looks like this. This is a plot of it. And notice something particular, that this function curves around in a circle. That means that if I were to make a closed loop, if I take a curve that comes back to the original place, then notice that I'm always pointing in the same direction as the force. That means on the way out, the work done is positive. On the way back, the work done is positive. This has no hope of canceling out to be 0. This is called a rotational vector field, and that is why the force is not conservative. What we're learning is that apparently this condition that we have to impose means that you can't have any net circulation of the field. I'll give you an example of something that doesn't have circulation. We'll go back to this example from earlier. Here, look, now I have my circle. On the way up, I do negative work. On the way down, I get some positive work. So here I get cancellation. This is irrotational, and this is conservative. It doesn't really matter which path I pick here. As soon as I see that it's irrotational, I know for a fact that both of these curves will produce the exact same work. Here is the quintessential irrotational curve. This is the real law of gravity. Well, real according to Isaac Newton anyway. And that we know is something that conserves energy. Why is gravity a conservative force that conserves energy? Because if there were ever an irrotational field, this is it. This is a drain, and everything heads straight for the drain. So not only when you go in a closed circle is it sometimes positive, sometimes negative, but if you go in a closed circle, mamma mia, you are always perpendicular to the force, and so it can't do any work. And so this condition is satisfied for this field, and that is why it is conservative. That means that you can go any path you want in a gravitational field. So long as you begin and end in the same two places, your change in speed will be the same. It does not matter which curves you take. You will have the same speed, change in speed by the time you get to the end. Okay, so to sum up, energy conservation means that the work done by a force is path independent. That is the real definition of conservation of energy. In one dimension, this means the force can only depend on position. And in three dimensions, it means that the force field has to be irrotational. Okay, hopefully this video was more helpful than confusing.